Penguin Random House Audio presents Space at the Speed of Light, the history of 14 billion years for people short on time. Read by the author, Dr. Becky Smethurst.
To you, whoever you are, for being curious enough not only to pick up this book, but also to open it. Oh, and to Dad, for reminding me not to become an accountant. Preface. The wondrous thing about science is that nobody knows the right answer. This is not how we are taught science as children, though. In the classroom, theories are presented as hard facts, which have always been understood in that way. Fortunately, the reality is far more creative. Being a scientist is like fitting in the pieces of an ever-changing jigsaw puzzle for which we've lost the lid. The work of so many people over decades, even centuries, slowly builds a picture of our current best understanding. While some areas of science still have the odd piece missing, some have giant gaps which we currently don't have the tools, the mathematics, or data to even glimpse what shape the pieces are. Science is all about posing the questions to which nobody knows the answers yet. Convincing people that there is a right answer based on evidence and facts you, your colleagues, and your predecessors have collected to build a theory of the previously unexplained is the crucial bit. This means that science moves quickly, with theories maturing and sometimes even boomeranging as more evidence comes to light. I therefore might have misled you, listener. The theories and facts outlined in this book offer a history of 10 big questions about space and how science currently answers them. They're all considered successes now, but who knows how they shall be perceived in 50 years. Perhaps our current theory of dark matter will be scoffed at by future generations, akin to our current disbelief that learned minds once thought that the Earth was at the centre of the universe, or that the atom could not be split. Yet that doesn't mean we shouldn't treasure this knowledge now and the wonders of our world that it lays bare. The chapters in this book cover the essentials behind the evolution of some of the most successful theories in describing the weird and wonderful objects in space, either for those who want new glimpses into its depths or have no prior knowledge of the secrets it contains. Listening to this book will take you on a tour of the universe, from its beginnings in the Big Bang to the elusiveness of dark matter to a thoughtful consideration of whether life exists beyond our planet. Now, if we linger when we reach black holes, that's because they are where my heart truly lies. My own scientific jigsaw puzzle, which I attempt while sat at my desk in the astrophysics department in Oxford, is helping to understand how these enigmas affect the galaxies they reside in. And we end with what we still don't know. The biggest question of all, really, and one we'll never be certain we've answered wholly or correctly. But as an astronomer, this is the most exciting quest of all, pushing the boundaries of our knowledge bit by bit to uncover a fuller picture of the universe and our place within it. My hope is that this book will give you glimpses of that as yet incomplete masterpiece. Chapter 1. Why Gravity Matters. The Sun is just one star in over 100 billion stars in our galaxy, the Milky Way. It's an island of gas, dust and stars more than 1,000,000 trillion kilometers across. At the center of the Milky Way star system, there's a black hole 4 million times more massive than the Sun. That's something we call a supermassive black hole. And like the Sun in our solar system, it's in the gravitational driving seat of our whole galaxy. Isaac Newton discovered the law that governs gravity some centuries ago. Two objects will attract each other proportional to how heavy each object is. The lighter object will be affected more by the force between the two objects. The force also depends on how far apart the two objects are. The farther apart they are, the weaker the force between them. So if you double their distance, the force drops to a quarter of its original strength. Now, with these laws, we can work out the effect of gravity between any two objects in the universe, including between you and the Earth under your feet. In case you're wondering, you feel a constant force of about 500 to 1,000 newtons, depending on your weight, from the Earth's gravity pulling on your body. Now, for context, the average force of a human bite is about 700 newtons, and a great white shark bite has a force of 18,000 newtons. The law of gravity brings order from chaos. It is, after all, what produced our solar system. Before the sun formed, there was only a giant cloud of hydrogen and helium gas with a sprinkling of heavier elements like oxygen, carbon, and iron left over from a previous generation of stars. This cloud was a swirling mess containing the atoms of each element. As each atom is a tiny particle of a certain mass, they were gravitationally attracted to all the other particles in that messy gas cloud. Those particles then started to clump together under gravity, with the biggest clumps attracting the other clumps, until eventually gravity overcame the energy of all the particles whizzing around and trapped them together to effectively cool them down. The next step was the collapse of the gas cloud down to a really high density, where the pressure increased so much that it got hot enough to ignite nuclear fusion, and our star was born. Nuclear fusion is when stars, like the sun, turn 4 atoms of hydrogen into 1 atom of helium. And it's why all the stars in our night sky shine. So what once was a swirling cloud of gas full of atoms whizzing around became a burning protostar because of gravity. Now, that endlessly whirling cloud of gas will also have been harboring a remnant of the past. It will have inherited some leftover rotational energy, which we call angular momentum, from a previous generation of stars, perhaps even the first stars to form after the creation of the universe. This means that overall, the gas cloud was swirling preferentially in a certain direction, so that as particles started to clump together under gravity, they assumed the same preference. The proto-sun began spinning. What happened to the rest of the gas cloud around the early sun is the same as what happens to a ball of pizza dough when you spin it above your head. It flattened out into like a saucer or a disc, which went on spinning. Inside the disc, the gravitational attraction between particles continued so that more clumps formed into protoplanets around the sun, giving us a beautifully ordered system where the planets, plus comets, asteroids, and all the other leftover bits of rock, all orbit around it in the same direction. And this process is how we think all stars, not only the sun, have formed. The same thing is reflected in our own Earth-Moon system. The Earth spins in the same direction as it orbits because the tiny particles that clumped together to make it had inherited that hint of angular momentum from the previous generation of stars. Similarly, the Moon orbits around the Earth in the direction that the Earth spins. But that's where the similarities stop, because the rest of the Moon's properties are consistently strange. Its day is as long as its year. That means the time it takes to spin around on its axis, its day, is the same time it takes for it to orbit the Earth, its year, which is 28 Earth days. If the Earth followed this example, half of the planet would always be in daylight and half would always be in darkness throughout the whole year as the Earth made one orbit around the sun. The Earth would spin at the same rate to always keep one side facing away from the sun. This is why we only ever see one side of the Moon. We never see its far side because it never points towards us. Now, that's not to say that the far side is the dark side, however, because the Earth doesn't light up the Moon, the sun does. This is why we see the phases of the Moon. We see a full moon when it's on the opposite side of the sky to the sun, which then fully lights up the side of the Moon pointing towards us. And we see a new moon when the Moon is between us and the sun, so the sun is lighting up the side that points away from us. If you are now wondering why we don't get a total solar eclipse every 28 days, considering the Moon passes between the sun and the Earth on each of its orbits, the reason is because the Moon is not orbiting in the same plane as the Earth is around the sun. It's slightly tilted by about 5 degrees, so sometimes it passes just below and sometimes just above the sun in the sky during its new moon phase. All of these properties of the Earth-Moon system might seem like happenstance, but they help to reveal something about how our moon formed. You might expect that the moon formed around the Earth in similar circumstances to how the Earth formed around the sun, i.e. from the leftover bits that didn't go into forming the Earth. But our best...
Sample complete. Ready to continue?